Hi, in this video I'm going to explain this idea of the fundamental calculus theorem, which I'm going to refer only by saying FCT. And actually I'm going to start by saying something. When I refer to the FCT for terms of purposes of this course, I'm going to refer to actually what is called the fundamental calculus theorem part 2, which is what actually we'll be going to be using here in this course. So okay, let's start by saying something. I have here a function f of x depicted here in three graphs, which is the same f of x, and I have a couple of point sets in here, the f of x, which is the value for x plus h, and these other x here. Now I'm going to say that these two values are separated away by a distance, which is actually h. And I'm starting by saying that everything I'm going to be using and saying all along this course would apply only for and when h is really small. So okay, now let's assume something. I'm going to assume that for in correspondence with this f of x exists a function which I'm going to call big f of x. I mean, could say capital F of x. I'm just going to say big f of x, and this big f of x, it's good for and will give us in return the area between this function f of x and a value on the x-axis. I'm sorry, on the x-axis. It will work for a couple of values, between a couple of values, just like the Riemann sums. But I'm going to start by saying only this. It will give us in return an area between this f of x and the x-axis. So let's start by saying something here in the graph as well. So if I calculate for this big f of x, big f function, I'm going to say big f of x plus h. So if we write this big f of x plus h, what we get in return would be the area between for f of x and between f of x and the x-axis, and that will be between the values of 0 and whatever will be x plus h. So we will get basically this area in return, this area here. So if I write now big F of x, I will get in return the area between this f of x and the x-axis between the values of x equal to 0 and whatever x is. So I will get, basically we will get this area in return. So if I subtract f of x plus h minus f of x, let's say if I subtract these two guys, what I would get in return will be essentially, well, actually this area, which is to say, in other words, I will be subtracting this area minus this area. So, but the thing is, as long as h is really small, we could say this is approximately the same as saying that f of x times h. Now this looks kind of weird, but what does it mean? This f of x times h is essentially something basically like the concept of Riemann sum. This is a rectangle. This is the height of the rectangle, and this is the width of the rectangle. But as long as h is really close to 0, this rectangle will be actually super thin rectangle. So we can use a trick here to make a better use of this expression. We could use a trick. If I divide by h both sides of this expression, I will get to this expression. F of x is approximately the same to f of x plus h minus f of x all over h. Now here comes the thing. When in mathematics you say that something is really close to another value, in this case h is really close to 0, it's another way to say, and it's a nice way to work this through in mathematics, that f of x would be equal to the limit when h approaches to 0 for f of x plus h minus f of x all over h. It's a very ugly h. There it is better. Now, here comes something very, very interesting. This is something that you should have seen before, and you should be very familiar, or at least or have some nightmares when you think about it. This is something that you call in differential calculus the concept of the derivative, and that's something really cool, because this is it's connecting actually the idea of the area between a function and the x-axis and the instantaneous rate of change, which is actually the derivative of the function. So basically what we can say, conclude between for this process that we did, is that in any case the function f of x will be equal to big F prime of x. So this is basically what we did here, this statement. If we take the derivative of this function that calculates the area between the function f of x and the x-axis, you will get back to the actual f of x where you started. And here I'm going to use a diagram. I'm going to use a diagram because I think it's better just to walk this through. So if I start here, I have here my f of x, I have here my big f of x, and I have over here a super well-known f prime of x. So in any case, you know, when we started in differential calculus, you could get from here this f of x to actually the f prime of x just by taking a derivative. Let's say we jump from here to here by calculating using a derivative. Again, if you take the derivative of f big F of x, you will move from here to the f of x. From here, it's a very ugly line. There it is. From here, f big F of x to f of x by taking the derivative. Now, if you want to do the opposite, the actual opposite here, that is to say, to move from big to f prime to f, or from f to big F of x, that is to say, move from here, you would use something called a antiderivative, and it will apply just the same. You move from f of x to big F of x, you will get from here to here by taking a antiderivative. And just as the derivatives, an antiderivative is just basically a set of formulas. I mean, you have several formulas that you will have to apply and to transform an f of x to a big F of x. I mean, from here to here, or in other case, from here to here. And well, that's basically the idea of the fundamental calculus theorem part 2. This is what we're going to be working during the semester and learning how to use it.